Hi everybody, this is Mr. Conti and welcome to my crash course in calculus video. As many of you are aware, the big difference between first year physics and AP physics is the fact that we'll be using calculus to solve more advanced physics problems. The issue is we start using calculus very quickly in the course, and with most students concurrently enrolled in calculus this year, it's my responsibility to give you guys at least a preview of some of the basic rules of calculus that we'll be needing to solve those problems. So this video is designed to provide you some background information and some essential rules that we'll be using to solve some of the problems at the beginning of this year. As we go throughout the year, you guys will get even more detail in your calculus class and hopefully become stronger in your abilities to utilize the rules that you learn in calculus. But this video is to give you a quick tutorial and some background information about what makes calculus important, and some of the basic rules that we'll be needing to apply to functions so that we can solve some of the more advanced physics problems. So here's an outline of what we're going to be looking at. The first topic that we're going to discuss in this video is finding slope. Now this seems like a simple procedure, but typically when we've talked about slope, even in my physics class, we talk about the slope of a line. You pick 2 points, use the slope formula, you get a value. But what if the function is not a line and it's a curve? Well, we've also discussed that too, and we talked about how a curve has different slopes. Depending on where you are on the curve, it could have a higher slope or a lower slope. And so the process of differentiation, which is fundamental in the first semester of calculus, is a method in which you use to find a function which describes how the slope changes on a curve. So we're going to be talking about that. I'll give you some background information of where this process comes from, but you'll see that we can simplify the process down into some basic rules which we could apply to different functions. The challenge is knowing when to use the rules, and so that can really only come with practice, but I'll give you guys some examples of where you might see these rules being applied. There are also some special cases of different types of functions which you should know what their derivatives are. So we'll go over what those special derivatives might look like. And the inverse of differentiation is a process called integration. So they are reverse processes. So if you're finding the derivative, think of that as going one way, let's say forward. Finding the antiderivative is like going backwards. And this process of finding the antiderivative, or performing integration, helps us to find the area under curves, which we also found in first year physics to be important to define certain quantities like displacement under a velocity time graph. So slope and area are related in this way. Slope can be found of a function if you take its derivative, and area can be found under a curve if you take that function's integral or antiderivative. So generally speaking, integrating tends to be harder than differentiating. So this definitely takes a lot of practice to getting used to. So I won't go through a lot of detail, but one of the tricks of integration is using a process called U substitution or U sub. So I'll show you an example of that, and then I'll close out by just previewing an example of something called a differential equation. In advanced math and physics classes in college, differential equations are used throughout. And these are equations that have derivatives in them. So think of, y equals 3x plus 4. That's an equation. But now, imagine that in that equation, you have derivatives in them. That's a differential equation. And over the course of the year, we'll see why these are important, but I'll let you guys see one example of this type of equation at the end here. Okay, let's get started by talking about slope. One of the first times we had to use slope last year is discussing the quantity velocity. We found that by plotting an object's position over time, that the slope represented on that graph was the rate of change of the object's position over time, which is by definition velocity. It's not only how fast the object's going, but because position also holds information about which way the object's going, then velocity includes the direction as well as the speed. So we know that if the slope is negative, that the object is still moving with some speed, but the direction that that object is moving is in the negative direction, however it is defined. So here's an example of a graph, and this is the common mathematical notation. So this is saying that x is a function of time. So x depends on time. T is the independent variable. So we plot that on the quote-unquote x-axis, the horizontal axis, and then x is plotted on the vertical axis, which is the quote-unquote y-axis. So the easiest type of graph that we've dealt with is a line. For us in our physics class, we would have said that this object is moving with a constant velocity. That's because the object covers equal distances or equal displacements in equal amounts of time. So if you pick equal time intervals, you can expect that an object moving with a constant velocity will cover the same displacement in that period of time. Now, if you want to find the rate of change of the displacement over time, on a line it doesn't matter what 2 points you pick. So here you can see these 2 points were selected. You would look at what the values on the horizontal and the vertical axis are. So this first point here is t1 comma x1, and the second point is t2 comma x2. The slope, which we usually say rise over run, is the change in position over the change in time. Delta x divided by delta t. That's velocity. Delta x represents the change in these two x values, x2 minus x1. Delta t is the change in time, t2 minus t1. this will get you a number, and that value represents the slope of this graph, which is the velocity of this object. Now let's take a look at this graph. This is a parabola. It's still a position versus time graph. We're still looking at a position function as a function of time. But it's a curve, not a line. So what we learned about this last year is that objects that produce a parabola on a position versus time graph are said to be accelerating or changing their velocity over time. The evidence of this is the fact that the slope is described to be changing over time. So unlike a line, the slope of this curve is never the same. We would say that at the very beginning, the slope is very shallow. At t equals 0, it's the slope is flat. The slope is equal to 0. But as you move along this curve, you see it getting steeper and steeper, and so the slope is increasing. So if I were to ask to find the velocity, you could jump and say, let's use this formula. I could still pick 2 points like I did up here and find delta x over delta t. Now, what that does is it finds the slope of a line. It's not the slope of the curve, but these 2 points plugged into this formula will find you the slope of the line that connects these 2 points. This is the secant line. The slope of the secant line determines what is known as the average slope, or in this case the average velocity, if you're talking about a position versus time graph. It is not the velocity, is not the slope, but an average which is representing just the time interval between t1 to t2. Now, as an average, because this is a constantly accelerating object, that means the object must go through every velocity, which represents every slope, between the slopes that you would find at the first point and at the second point. So this being the average slope is a slope somewhere in between these 2 points. The slope at the first point is small compared to the slope of the second point, which is steeper. It's the larger slope. So the average should be somewhere in between. We can use a process which is called the limit to find the location within this interval where the slope of this curve matches the slope of this secant line. And visually, how I can try to show that to you is by taking these 2 points and moving them closer together. Now, what I've done is I made the interval delta t smaller. It is no longer the interval between t1 and t2. It's an interval that's smaller. And so the average is still the same because it's still producing the slope of the same secant line, but the interval of time is smaller. So you can see that I can bring these 2 points closer and closer together, always along that curve, and I eventually find a place where the points overlap. And so that means that this line is only touching the curve at this single point. And I've reduced my time interval, delta t, to 0. There is no separation between these 2 points. They're on top of each other. So delta t, so there's no difference between t1 and t2. So t2 minus t1 is 0. So there is no difference between those 2 times, and so delta t is 0. So the slope of this secant line is the slope of the curve at this point. Whatever this point is, this slope represents the slope of the curve at that point. Well, in terms of physics, at this time, whatever the average velocity was between time t1 and t2, this is the velocity at this moment in time. And so we call that the instantaneous velocity of the object. Now, how could I figure out what the slope of this line is based on this one point if delta t is 0? I can't find the slope using this formula, because if delta t is 0, I get an undefined answer. And there's clearly a defined answer, because all you have to do is separate these 2 dots just a little bit, and you'd have numbers that you could plug into this formula. But if you make them go on top of each other, bringing delta t to 0, you get an undefined answer. This is where calculus comes in. So let me show you some notation. We want to undergo this process to find the slope of the curve at a single point. So we're going to use this process that we call the limit. We're going to write LIM for the abbreviation for limit, and under that we write delta t with an arrow to the right, 0. This reads the limit as delta t approaches 0. So you write this to represent this. So if I write the limit as delta t approaches 0 of delta x divided by delta t, what I'm saying to do is find delta x divided by t as we let delta t get closer and closer to 0. So that is the process by which we take these 2 points and bring them closer and closer together. It's only when delta t actually gets to 0 that you find the slope at that one point, which is the slope of the tangent line. Here's our first example. X at t equals 3t. This is a linear function. Because it's linear, we can refer back to this first graph, which shows the straight line, that this is constant, an object moving with constant velocity. So if I ask you, what is the velocity of this object? Well, because it's constant, I know that it's just a number. What is that number? the velocity is represented by the slope of this function. Well, I don't need any fancy formula to work it out, because I can just look at this equation and know that that 3 represents the slope of this line. So what is the velocity? The answer is 3. So it's a 3 meters per second, for instance. That's how fast this object's going. Doesn't matter what time it is. No matter what the time is, the velocity is always 3. So because we know how fast it's moving, I can tell you at any time what the position of that object is. But since we already know what the answer is, we know that the answer is 3. What I want to do with this example is use this example as a means to look at how you would use the language of calculus to get to the same result. And you'll see that it's a lot of work for little reward, because we already have the answer. But let me show you how to take the limit. So rather than use the graph that we started with, what you typically learn in calculus is that if we take this first point, we're going to say that that point occurs at time t, and the corresponding x location is x evaluated at that moment in time t. Okay, so that makes up one point. To find another point, what I do is I take the first time and I add some interval, delta t. So rather than call this t1 and t2, I'm going to call this t, and then I'm going to call this t plus delta t. So this is this much time after this time. And so this x coordinate corresponds to the x position evaluated at the moment of time t plus delta t. So we want to find the slope of the position versus time graph. So we take the limit as delta t approaches 0. And if we go back up to our definition here, we want to find the limit of delta x over delta t. So here's how we rewrite that. Delta x is the second position minus the first position. So if you remember from this picture, that first position is x evaluated at t plus delta t, and the first point is x at t. So you want to just subtract those, and that'll get you delta x. So this is delta x divided by delta t. So literally what this means that we have to do is, if we want to plug our information in example 1 into this formula, notice that what we have here, x at t, is the formula that we were given, 3t. So we're saying here that x at t equals 3t. So I can substitute in for x at t 3t. But what about this? Well, it says first to evaluate x at t, evaluate the position, instead of t, evaluate it at t plus delta t. So wherever there's a t, I'm going to replace it with t plus delta t. So let's do that. Okay? So in this first term, I take it, instead of 3t, it's 3t plus delta t. So that's this first term. Minus, in for x at t, is just 3t. And the bottom stays the same. Notice that I keep writing limit as x approaches 0, because I haven't done anything with that yet. Now I can simplify. I know I could distribute the 3 here, and then I can subtract. and see what I have left over. So we get 3t plus 3 delta t minus 3t. These two terms will cancel out because 3t minus 3t is 0. And what I'm left with is the limit as delta t approaches 0 of 3 delta t over delta t. Now because there's a delta t on the top and the bottom, they cancel out because delta t divided by delta t equals 1. So there's no delta t to approach 0. And so you essentially don't have to use this at all in this problem because the delta t disappears. And all you're left with is 3. And so this shows you that no matter what the time is, the limit, the slope is always going to be 3. So if we do a different example, you're going to find that this delta t may not disappear entirely. If that's the case, the very last step is to perform this limit by taking whatever terms have delta t in it and setting it equal to 0. Because that's what in order to find the slope, or in many cases the equation which represents how the slope changes, what you're going to want to do is set delta t equal to 0 only once all the simplifications have been done. Alright, here's example number 2. So just like at the beginning, I gave you guys a parabola. So that could be represented with this formula, for example number 2, where x of t is equal to t squared. It's a quadratic. We know from our experience in first year physics that quadratics that have a t squared term are objects that experience constant acceleration. That means that their velocity changes at a constant rate. So their velocity is no longer constant, but because the velocity is changing at a constant rate, then we can say that the acceleration, the change in velocity over time, is a constant. You might remember the formula 1/2 at squared. So the t squared term tells us that it's an object who's experiencing constant acceleration. If it was a t cubed term, for instance, then that object in a cubic would be experiencing a changing acceleration. And that's something that we will see this year. But we already know that there's no such thing as finding the slope of this function because it has no single slope. So what will this limiting process do for us? Well, it will tell us how the slope changes as a function of time. But we already know what that means. The slope function is going to be the velocity function. It's going to tell us how the velocity is changing with respect to time. So by finding the limit of this function, we are essentially finding the slope of any tangent line depending on what time you choose, which will give us information about how the velocity is changing as a function of time. So let's go ahead and perform the limit process with this function. So we first start out with our formula. This time I'm telling you guys that the velocity function is, by definition, the limit as delta t approaches 0 of the change in position over the change in time. So now we are going to make our substitutions. plugging in into our formula here, our equation, wherever there's a t, we're going to first plug in t plus delta t, then subtract the equation as is and divide it by delta t. Now, the next step is to simplify. It's a little bit more, there's a little bit more to do with simplification here, because now you have this term squared. And you can imagine that the higher the power of the polynomial, the more work you're going to have to do. And so this is where in calculus people start to get a little anxious having to do this all the time, but you'll see that our derivative rules are going to help eliminate having to follow through with this process all the way, but we want to make sure that this process works as well. So let's evaluate this by foiling the t plus delta t terms, and then we can try to simplify. Okay, so by foiling it, you get t squared plus 2t delta t plus delta t squared. So that's this term, minus t squared. But because I have a t squared and a minus t squared, they cancel. So then all I'm left with is 2t delta t plus delta t squared divided by delta t. Now, the good news is there's a delta t in every term on top. The two terms that are left over on top, there's a delta t here and there's two delta t's over here. So you can factor out a delta t from both terms, which is what you're seeing here. So if I factor out a delta t from both of the terms, I get 2t plus delta t. So now that I factored that out front, this will cancel with the delta t that was on the bottom. So they cancel out, they get you 1. And so all I'm left with here is the limit as delta t approaches 0 of 2t plus delta t. We have a delta t term left over. So now we get to use this limit term. So finding the limit as delta t approaches 0, we can do that by setting delta t equal to 0. And there we have it. With delta t equal to 0, all you're left with is 2t. So given a position time function, which I can actually, given a position time function of t squared, the corresponding velocity time function is 2t. So what this allows us to do is find the velocity or the slope at any moment in time of the position time function. So if I ask what is the slope of t squared at t equals 1, well, I plug in 1 in for t here. 2 times 1 is 2. The slope is 2. What is the slope of the t squared function at 3 seconds? I plug in 3 here. 2 times 3 is 6. So the slope is 6. So this object is moving with a velocity of 6 meters per second after 3 seconds. Why? Because the velocity increases at a rate of 2 meters per second every second. Now a quick word on notation. What this 2t represents is the derivative of t squared. So we would say 2t is the derivative of t squared. It is what you get through this limit process. Instead of writing the limit, we can eliminate the need to write the limit by first replacing the deltas, which, if you remember, actually is the letter D in Greek. We replace the deltas in our formula with the letter D for derivative. So the slope of x at t can be written first as the limit as delta t approaches 0 of delta x divided by delta t, or you can remove the limit entirely by replacing the deltas with d's. And so you could read this as dx over dt. So this is an acceptable way of writing the slope of x as a function of time. Sometimes it's also appropriate to pull the x out, and this d by dt term out front is often known as the derivative operator. So an operator is something that operates, acts on a function and causes it to do something else. So when I take the derivative operator, d divided by dt, and I apply it to x at t, it gets me the slope of x at t. So that's another way of writing it. This is common, but this is also used. Another way of writing it is using the prime notation. X prime at t is the same as dx over dt. This is the derivative of x at t. I could also say that the derivative is the velocity function. Specifically, the derivative of the position function is the velocity function. Alright, so these are all notations that you will encounter at some point. By the way, I wanted to make sure that I stuck with my x versus t. That's what we're going to be using a lot. We might use y at t, z at t, but it's likely in calculus that you're going to start out by using y as a function of x. And so I wanted to make sure that you can get used to using different letters as different variables and not just the standard x and y. Alright, on to the derivative rules. This is going to be important. These are the basic rules of taking derivatives without having to go through the tedious process of finding the limit, and which, if there's multiple terms in your function, that could get very tedious. If the polynomial is has a very high power, that can get very, very tedious. So I'm going to share with you the shortcuts, basically, of how to successfully find your derivative function with a couple basic rules. So this, generally speaking, this first rule that I'm going to give you is like the holy grail of derivative rules, because students who are not enrolled in AP Physics taking calculus will have to suffer through finding the limit and going through that whole process. But by using this first rule, again, we can bypass that, and so clearly gives the AP Physics students a bit of an advantage. So this first rule is called the power rule. It essentially helps to avoid having to use the limit definition. This works for any polynomial of any power except for to the power 0. Alright, so let's take a very general example. My function x of t equals t to the power n, where n can be any value except for 0. Because if it's 0, then the function is 1, and we already know that the slope of a number, the number doesn't change, and so therefore the slope must be 0. But we'll come back to that. This is just like our 3t example, except forget the coefficient of 3. So if I just had x equals t, t is just n to the n equal to 1. It's also t squared, where n equals 2. If this is your function, then the power rule says that the derivative of your position with respect to time is equal to the power of your polynomial n times t to that power minus 1. N has to be a real number and not equal to 0. Those are the only restraints. It has to take this form, so it has to be your, if t is your independent variable, it has to be t to some power, and that power must be real and not equal to 0. If that's true, then the derivative of that function is just the power times t to the power minus 1. That is so much easier than what we had to do with the limit process. And we're going to go over the example that we've already done and show how this rule can be applied to get the answer in a much faster way. But first, let me show you two more rules that are very basic, but they need to be said. The second rule is the multiplier rule. Let c equal a constant in this example. So it's just could be any number. Then if I take the derivative of that constant times my function, then that equals the constant times the derivative of my function. So what this basically says is that if you have a constant multiplying your function, then it doesn't matter, then the derivative of the product is equal to that constant times the derivative of that function. So again, it basically says you can remove the constant, find the derivative, because we're assuming that maybe this x of t is something like this. So imagine this being c t to the n. Well, I know that the derivative of x of t, which is where x of t is t to the power n, is nt to the n minus 1. So the derivative of c t to the n would be the same thing as our derivative here, but then we can just bring the constant along for the ride. So multiply that in later. So I'd put a c out front of here. Cn t to the n minus 1. Alright, so that's a really simple rule. If you have a constant out front, The constant just tags along for the ride. You multiply it in after you've taken the derivative of the actual function. The third rule is the sum rule. If I have two functions that are being added together, this could be like a t plus t squared. They're two separate polynomial terms. I want to still be able to use this rule. So this rule could act on both my terms separately. So that's what we do. If I want to take the derivative of a sum, I can just find the derivative of each term of that sum and then add them all together. So the derivative of a sum is the sum of the derivatives. Right, with these three basic rules, we can already tackle some very important types of functions which range from all different types of polynomials. So starting out with the basics, let's go back to our first example, x at t equals 3t. What is v at t? What is the velocity function? Well, again, we could say that this object has a constant velocity. How do I know? Because it's a linear function. It's the slope times time. So the velocity is not, it's really a weak function. It's a constant. It's a number. So it just has the value 3 the entire time. But how can I prove that using calculus? Well, we did this with the limit example, but now we're going to use our basic rules that I've outlined to show that the derivative of 3t is in fact 3. So which rules would I need to apply? There's two rules that I have to apply. I have a polynomial term, t, which the power n is equal to 1. You don't see it. And I have a coefficient out front, so that's the multiplier rule. So I have to apply both the power and the multiplier rule to this. So if I want to find the v at t, that's the same as finding the derivative of the position with respect to time, which is finding the derivative of 3t with respect to time. So the multiplier rule says, let's take the 3 outside. So let's not worry about the 3 right now. So I put the 3 out front. And so all I have to do is find the derivative of t with respect to time. So power rule says that if I want to find the derivative of any polynomial function with respect to some given variable, I determine what its power was. I bring that power down. So it's that power times t to the power minus 1. So I get 1 times t to the 1 minus 1. Well, 1 minus 1 is 0. T to the 0 is 1. 1 times 1 is 1. So the derivative of t is 1. That's just like saying the slope of x equals t is 1. So then I plug that back in here. So then I multiply through by the multiplier, like coefficient here. 3 times 1 is 3. So the derivative of 3t is 3. Alright, go back to example number 2. What is the derivative of t squared? Or what is the velocity function that goes with the position function t squared? We already know the answer. The answer is 2t. How do we use calculus and our derivative rules to determine that? Well, the only rule that seems necessary here is the power rule. So we only have t to a power. There's no coefficient. There's no multiple terms. So we can get away with finding the derivative of this by just simply using the power rule. So we write that in order to find the velocity, we must find the derivative of the position with respect to time, and that's the same as finding the derivative of this t squared term with respect to time. Applying the power rule, we bring the 2 down, bring the power down, and then we subtract the power by 1. And so you get 2 times t to the 2 minus 1. 2 minus 1 is 1. There's no need to keep that there. And so we're left with 2t, and that's what we know the answer to be. Let's try a new example. This example, number 3, gives us a position function equal to 4t cubed plus 2t squared. And your task is to find the velocity function. That's the same as asking for the derivative. It's the same thing as asking for the slope of the tangent line at any time along this curve. So if you'd like to try it on your own, I would suggest to pause the video and give it a shot, and then push play when you're ready to see the solution. Alright, so if you've tried it, let's talk about what you had to do to get your solution. Well, first of all, the rules that need to be used. We have a sum with multipliers and powers. So all 3 rules will need to be applied to solve this problem. So we're finding the derivative of our function. First, we use the sum rule, that we separate the 2 terms of the sum and show that we're going to find the derivative of each term. We're then going to use the multiplier rule, which says take that constant and remove it from the problem for the time being, because then we can just multiply it in back later. Lastly, we use the power rule. So we're going to use the power rule. We've already done the t squared, so we know that that's 2 times t to the 2 minus 1. If we do t cubed, the 3 comes out front. We have our t, and then we subtract the power by 1. So you have 3 minus 1. And then we simplify. Whatever we get once we simplify, that's the solution. That's the derivative of our original function. So simplifying our powers first, we get this, and then finally multiplying through by our coefficients, we get 12t squared plus 4t. Did you get it right? Good job. Alright, on to our next rule. I've already alluded to this. It's called the constant rule. The slope of a constant is 0. Because you think about what that graph would look like, the slope of a constant is just a horizontal line. And so the slope of a horizontal line is 0. So any constant all by itself is not dependent on time, and so therefore it doesn't change with respect to time, and so its derivative is 0. Here's a great tip that will help to solve many useful problems for us. If you want to find where the slope of a function is 0, that's the same as saying where the function is flat, or where the slope is 0. That's where the derivative is 0. Because when we talk about slope and derivative, those are basically interchangeable. So if you're looking to find the value where the slope is 0, you take the derivative and you find where the derivative equals 0, because if the derivative is 0, that means the slope is 0. So let me show you an example of where this tip will be helpful. This is going to be example number 4. So it says an object moves in the following way. We're given a position function. It's equal to 5t minus 2t squared, and t is in seconds, x is in meters. So this is a typical way that a kinematics problem might start. So what do I know right off the bat about this object? The highest power is a 2. So that means this object is an object that is got a constant acceleration. There's a couple other things that we can look at this and know right off the bat, but I'll use class time as more of a way to discuss those details. But you could look at this and tell me what the acceleration is, and tell me what the initial velocity is, and whether it's speeding up or slowing down at different time intervals, but we're going to talk about that in class. But my question to you is, at what time, if any, does the object come to a stop? Okay? At what time, if any, does the object come to a stop? Well, what does it mean if an object comes to a stop? That means that the velocity equals 0. But the velocity is the derivative of the position function. So this is where we could use this tip. If I were to take the derivative of my position function and set it equal to 0, I can find the time where this object would come to a stop, when that object has a velocity equal to 0. So we have our task. Find the derivative, set it equal to 0. You can try that on your own now. It's going to be, again, a combination of all 3 rules: sum, power, and multiplier. So you can pause the video now to double check to see if you can get the derivative on your own. So the derivative of 5t is 5 minus the derivative of 2t squared is 4t. So the velocity function is 5 minus 4t. So now we're going to set this equal to 0, solve for t, and that will give us the time when the object comes to a stop. So I can add 4t to both sides, divide both sides by 4, and I get that t equals 5/4 seconds, or 1.25 seconds. So this is the time that if I were to plug this into my velocity function, it would get me v equal to 0. Now, if I had gone up here and I'd asked at what position does the object come to a stop, I want to know at what location in space the object occupies when it comes to a stop. That is asking for the value of x. But now that I know the time, I can plug in this time into my original x at t formula to find the position that the object has at this time. But this time is special because it's the time when the object stops. Okay, we're going to address another 2 other rules for derivatives, which will help us to answer this question. how would we find the derivative of either of these two functions? All right, so the way I want you to look at this is I have these two terms, these two polynomials. What if I wanted to find, so each of these separately are straightforward with our three basic rules that we've, or five rules, or sorry, four rules: the power, multiplier, sum, and constant rules. You could use those four rules to find the derivatives of either of these polynomials. But what if we took the two polynomials and either multiplied or divided them by each other? And then I asked to find the derivative of that product or quotient. That's going to be a lot more challenging. Multiplying through is just tedious work, and then to divide, that might not even be really feasible in any sort of way. So how would I go about finding the derivative of either of these two problems, either the product of two polynomials or the quotient of two polynomials? Well, luckily, there are two rules. One, known as the product rule, applies to such a problem where you have the product of two functions, and then there is a quotient rule where you have two functions that are being divided by one another. So what are those rules? And so I'm going to show you what the rules are and how they can be applied to certain examples. So let's start with the product rule. For notation purposes, our function is going to be a product of these two functions, g times h. So g is a function of time, h is a function of time, and our function f is the product of these two functions. So what is the product rule? This is the product rule. The product rule says that if you want to find the derivative of f, which again is a product of these two functions, take the first function, multiply it by the derivative of the second function, and then add the derivative of the first function times the second function. So remember how we said we could easily find the derivative of either one of these two polynomials, but having to expand it all and then do it, that would be a lot more tedious. Well, you don't have to do that. The derivative of this, for example, would be this polynomial times the derivative of this polynomial plus the derivative of this polynomial times this polynomial. Let's try an example. So this is example number 5, where the function is t plus 4 times 2t plus 3. Now, because this is an easier product to FOIL than this one, let's go ahead and FOIL this so we have another way of confirming that this product rule actually works. So if you FOIL it, you get 2t squared plus 11t plus 12. The derivative of that is 4t plus 11, and the derivative of a constant is 0. So the derivative is 4t plus 11. So we found our derivative of our function not by using the product rule, but by actually FOILing this product and then taking the derivative using our previous basic rules. But now let's try to use the product rule here And you be the judge whether you think it's easier using the product rule or foiling it out and doing it the way we just did it. There will certainly be times where product rule will be maybe the only feasible way to get your derivative, but this one, you may argue one way is easier than the other. Okay, so this is like the t plus 4 is like my g function, and my 2t plus 3 is like my h function. So let's apply the product rule to this function. So the derivative is the first function times the derivative of the second plus the derivative of the first times the second function. Okay, so we're going to have two derivatives that we have to take. Then we'll have to simplify, and we're hoping to still get 4t plus 11. That's what the derivative should be. So the derivative of 2t plus 3 is 2. So you get first function times 2 plus the derivative of t plus 4 is just 1. So you get 1 times the second function. Simplifying, you get 2t plus 8 plus 2t plus 3. 2t plus 2t is 4t. 8 plus 3 is 11. The derivative is 4t plus 11. So, the product rule in this example may seem to have been a little more challenging, but it only looks challenging because doing FOIL with this wasn't too bad. But I guarantee you a lot more mistakes can come up if you're trying to factor distribute any of these together. The next rule is the quotient rule. That one's a little more challenging than the product rule, but again, sometimes it's necessary, and it's certainly going to be something that you'll have time to work on in your calculus class to get used to. But again, just giving you a preview of what that rule looks like. So for this, the quotient rule, we're going to take our same g and h functions, but now we're going to divide them by each other. So this is the quotient rule. Okay, it looks more intimidating, but it really isn't too bad. There's just a matter of the order of certain things that does make a difference. So I'm going to give you a little fun way to remember this. So first of all, the quotient rule is a quotient as well. So there's a top and a bottom. The top looks very similar to our product rule, where we have multiplying one of the original functions by the other derivative, and vice versa. The one big difference is that there's a minus sign. Instead of plus, it's minus. Now, because there's a minus sign here, it does matter which order these terms come. If you put this term first and then subtracted this, you're going to be off by a negative. So this order does make a difference. The other difference is that we're dividing the entire top by the h function, which was already originally found in the bottom, but we're squaring that whole function. So here's a catchy saying to help you remember this rule. So let our g and h function, let g be the high function because it's up top, and let h be the low function because it's on the bottom. And whenever we see the letter d, that just stands for derivative. So the saying goes, low d high minus high d low, square the bottom, and away you go. So the low function here is h. D high is the derivative of the top function, g, minus the top function times the derivative of the low function. And then you square the bottom. Low d high minus high d low, square the bottom, and away you go. So hopefully that will help to keep some of the terms straight. So for example 6, we're going to take the two g and h functions that we had before, but we're going to divide them through instead of multiplying them. Okay, so to get us started, take our low d high minus our high d low. We're squaring the bottom. Away we go. So we have all the right terms in their right positions, and so now it's just time to take some derivatives and to simplify as best we can. Don't expect the finished product to be anything really nice and tidy. You might have terms that just won't simplify any further, and that's okay. The point is to get this simplified as much as possible. So derivative of t plus 4 is 1. Derivative of 2t plus 3 is 2. We multiply this through, and we find that there are two separate 2t terms, that one is being subtracted, so they can cancel each other out. And 3 minus 8 is minus 5, and so we're left with minus 5 divided by 2t plus 3, the quantity squared. And that's our derivative. That is the derivative of this quotient. So remember, this function represents the slope of the tangent line at any time along this function. How about something like this? Example number 7. X at t equals 4 times the quantity 3t plus 2 to the power 25. So this would actually be a pretty difficult problem to solve with only our current rules. We essentially at this point would have to FOIL this out. It's got 25 terms, and so it's a polynomial with 25 terms. That's going to be quite a challenge to, well, actually 26 terms. That would be quite a challenge to do, and very tedious and time consuming. It could be done, but there's got to be an easier way. And there is, in fact, another rule that will help us get through this. Now, first let me show you that if this was rewritten a little bit differently, it'd be a different function, but if it was written just slightly differently, it would be a pretty simple problem to solve. If inside the parentheses, instead of having this linear function, 3t plus 2, where you have a sum and multipliers in there, let's just say what was in parentheses, let's set that equal to t. If that was the case, there is no issue with this problem whatsoever. It's just you have a multiplier, which you can multiply in later, and then it's the power rule. Even though it's a big power, it's just the power rule. So we can take the derivative of that very easily. You bring the power down, so 25 times 4 is 100, and you subtract the power by 1, so it's the 24th power now. We're done. So how could we utilize this piece of information? Somehow, if I could replace 3t plus 2 with just a single variable, I'd know exactly what to do. Well, that's where this process called the chain rule comes in. The chain rule's good to differentiate functions that are inside of other functions. So when you have a function inside a function, a composite function, chain rule is good. So how can we compare that to what we have here? This is one function, and this is something that we could easily differentiate. This is the 3t plus 2 is essentially a function inside of this function. So we can solve this problem using chain rule by utilizing our knowledge of taking the derivative of something like this. But obviously these are two different functions, so what will the difference be? So let's look. So we're going to use a process called U substitution, or U sub for short. We're going to replace this 3t plus 2 and just call that U. We're going to substitute in the letter U for this whole thing, because then instead of a t here I could put a U, but that would be the same thing. It's just U is my new variable. But switching the variables over requires some other manipulation, some other things to multiply through in order to make sure that everything checks out right. So now U is going to be a function of time, because we're going to set U equal to 3t plus 2. And now x is going to be a function of U, right? But since U is a function of t, then x is still a function of t. So it's just because of that. It's like the Russian nesting dolls. It's one function inside of another function. So, but it looks so much better this way, because you know you can take the derivative of this thing. But we'd be taking the derivative of this with respect to U and not with respect to t. And the essential problem, the essential question that we're trying to answer is the derivative of our x function with respect to time. Not with respect to U, but with respect to t. So, yeah, I could say that the derivative of this is 100u to the 24th. But that is the derivative of x with respect to U. How do I get it back to the derivative of x with respect to t? So the chain rule gives us the connection here. What we want is dx divided by dt. That's the derivative we want. By taking the derivative of this with respect to U, that we would know how to do, that would give us dx divided by du. So that the chain rule, chain comes from the fact that there's another term here. We're linking another link of the chain, which needs to be multiplied to this term to get us back to this. Take a second and think to yourself, what do I place in that parentheses? What would I have to multiply dx by du by to get dx by dt? The answer is du by dt, the derivative of U with respect to t. Why does this work? Because look, you have a du up top and a du on the bottom. If you multiply these two things together, the du's will cancel and you're left with dx over dt. So this product is the same thing as dx by dt. So where we can easily find the derivative of x with respect to u, we can find dx by dt by taking this derivative and multiplying by another derivative, which we haven't done yet, but we can easily do. We can easily take the derivative of our u function with respect to time. So our u function, 3t plus 2, the derivative of this with respect to time is just 3. So dx by dt is our derivative of x with respect to u, which we got 100u to the 24th, times du by dt, which is just 3. So I can multiply 3 times 100, 300. But only thing we'd have left to do is to remove the u from this formula, because the original function x has t in it. And so we want to see the t back in our equation again. So all you have to do is substitute in 3t plus 2 back into u. And so the final derivative is 300 to the times the quantity 3t plus 2 to the power 24. And that is the application of the chain rule. Example number 8. Your task is to find the derivative of the function 2 divided by 4t squared plus 7. I want you guys to take a moment on your own and try to work this out. Be sure to think about all the possible rules that we've gone over and try to figure out what rules you might want to use to solve this problem. Let's review all of the rules that we know so far. We have the power rule, the multiplier rule, the sum rule, the constant rule. Then we have the product and quotient rule, and then we have the chain rule. So, what rules would we use to solve this problem? Well, we know that the first 4 have to be used. That's a must. We have a power. We have our 4 as our multiplier here. We have the sum down here. We have our constant, which is 7. We have the constant up there, which is 2. So there's definitely a need to use all 4 of these. The question is, what other rules might be useful here? It looks as though quotient and chain rule might both be possible ways that we could solve this problem. So let's take a look. So we can use the quotient rule if we use the function as it's written, because you have the 2 as the numerator and then you have the rest of the function, which is the denominator. But you could use the chain rule if you rewrite the function like this, because you can remove the denominator by taking that denominator and raising it to the power -1, which brings it into the numerator. And so now we have a situation like we dealt with before, where we could use u sub and then do a more simple power rule with the u sub function. But let's try the quotient rule first. Remember our saying, low d high minus high d low, square the bottom and away you go. So low d high, the derivative of 2 is just 0, minus high d low. So the derivative of this is 8t plus 0, so just 8t. And then you square the bottom. So there we have our derivative. This is 0. This is minus 16t divided by 4t squared plus 7, the quantity squared. Not too bad. Alright, you remember the saying, the quotient rule isn't too tedious. Now let's try the chain rule. So first, to use chain rule, we had to rewrite the function with the denominator up into the numerator by using the power -1. Now we have to choose our u function. So we set u equal to 4t squared plus 7. So now that x at u is equal to 2u to the -1. That's a pretty straightforward power rule slash multiplier rule problem. But remember, the other derivative that we'll need is the derivative of u with respect to time. That derivative is 8t. The chain rule says we take the derivative of this and multiply it by this. And then we have to make sure we get the u's out of the way. So, derivative of x with respect to u. Bring the power down and multiply it by our multiplier, so you get -2 u to the -1 minus 1. Well, -1 minus 1 is -2, which could also be put back down in the denominator as a u squared. So you get -2 divided by u squared. So that is dx by du. The chain rule says dx by dt is dx by du times du by dt, which is -2 divided by u squared times 8t. But remember, we have to substitute back in u equal to 4t squared plus 7, and we get dx by dt is -16t divided by 4t squared plus 7, the quantity squared. And that's, in fact, what we got by using the quotient rule as well. Alright, so there are two viable ways of getting the same result. It's essentially up to the problem solver how quickly you recognize the process one way or the other. It's up to the person to decide what way they like to do it better. You now know all the essential rules of finding derivatives, but there are still special derivatives that I will not be proving to you guys, but instead just telling you what those special functions derivatives are. And so they include trig functions, exponential, and logs. And there's also some basic algebraic rules for logs that you guys need to know as well for certain problems that we do. So, again, I'm not going to give you any background knowledge of why these derivatives are the way they are. You might address that in your calc class. We might address that at some point throughout in the year where it becomes more relevant. But for the time being, I'm just going to tell you what these derivatives are, and I'm only going to tell you the ones that show up more or less in what we do. So the first two functions are the trig functions, sine and cosine. The derivative of sine is cosine. The derivative of cosine is minus sine. That's it. One function describes the derivative of the other, but don't forget this minus sign. So if you start with a sine function and I ask what is its derivative is cosine. If I start you out with cosine and I say what is its derivative, it's minus sine. You should know that E stands for Euler's number, which is some really long irrational number that starts out as 2.718 and keeps going on infinitely. The natural logarithm, ln x, is the same as the log of base e of x. If y equals the natural log of x, then x equals e to the y. So when you have a log whose base you know, so in this case the natural log, it has a base, its base is Euler's number e, then y represents the power you raise e to, and x represents the answer. So you can essentially unlock what x is by taking the raising each of these up into the power of some base e. So e to the y equals e to the ln x. E to the ln x is equal to x. My favorite derivative, the derivative of e to the x, is e to the x. No, that is not a mistake. It is in fact e to the x. So that is the only function that, no matter what derivative you're talking about, you can keep taking derivatives of that function forever, and it's always the same function. Less common is if you have a constant to the power x. So like 3 to the power x. Its derivative, similar to the e to the x, you have that c to the x term, but you have to multiply that by the natural log of that constant. Another interesting derivative is the derivative of the natural log of x. The derivative of the natural log of x is defined as 1 over x. Alright? So again, we're not going to go into any further detail on why that is, but you can prove it if you want to graph ln x. You can find the slope of the tangent line at any point along ln x by just plugging in a value of x into the derivative. Now, natural log has a base e, so this log is a base of some constant c. So if I take the derivative of this function, I get 1 divided by x, just like the natural log, but then I have to multiply that by 1 over the natural log of the constant, which appears as the constant here. Alright, so there we have some calculus rules for logs and exponentials. But now let me review some other useful properties of logs that we will need to use. So we have that the natural log of x times y is the same thing as the natural log of x plus the natural log of y. The natural log of x divided by y is the same as the natural log of x minus the natural log of y. The natural log of x to the n is the same thing as n to the natural log of x. So this has nothing to do with calculus. These are just basic properties of logs. And the natural log of 1 over x is the same as minus natural log of x. That makes sense because 1 over x is x to the minus 1. And with our power, you get the minus 1 outside. So now let's try some examples out that utilize these new special derivatives and properties that we have at our disposal. So the first example here, example number 9, is x of t equals a times the sine of omega t plus phi. This is the general form of a wave function. We'll learn later on in the year where a stands for the amplitude of the wave, omega is the angular frequency, and phi is the phase constant. But my question is, what is the derivative of this function? A, omega, and phi are all constants. They're like numbers. So with that in mind, what is dx by dt? So if we think of all the rules that we need to use, we have our special derivative rule for sine, but it's not just sine of t. You have a function in a function, so that's a chain rule. And then we'll have to use the power rule, multiplier rule, constant rule. So there are certainly a number of rules that we'll have to use. So we'll let our u be equal to omega t plus phi, so that our x at u is now a sine of u. Remember, we have to take the derivative of our u function. We get omega. We take our derivative of our x function with respect to u, and the multiplier rule says to just bring the a along for the ride, and our sine rule says the derivative of sine is cosine. So there we have our derivative. Chain rule says we have to multiply these two things together. Du by dx times du by dt. But we remember that u is actually omega t plus phi. And so we get the a from here times the omega from here, cosine of omega t plus phi. That's the derivative. Example number 10. Find dx by dt of the function e to the t squared. Okay, so we know we're going to have to use the exponential rule, but a chain rule is necessary because it's not just e to the t, but if it was, that's an easy derivative to take. But we could substitute in u for t squared and follow through with the chain rule procedure. So we let u equal to t squared, so du by dt, we use the power rule, is 2t. My favorite derivative, once we make the u sub, the derivative of our x with respect to u is the same thing as x to the u, which here is e to the u. We multiply these two derivatives together, but we plug back in what u was before. So we get that the derivative is 2t e to the t squared. Example number 11. We have x of t is equal to t cubed times cosine of t. So here we have a product of two functions. So let's use product rule. So in order to use the product rule, we'll need to take the derivative of each of these at some point. So this one is just power rule. Here we'd have to use the cosine rule, where cosine of t is minus, the derivative of cosine of t is minus sine of t. So product rule, we take the first function, multiply it by the derivative of the second, plus the derivative of the first function times the second function. There's not much in the way of simplifying this down any further by just bringing that negative out front. Example number 12. X of t equals the natural log of t over t plus 1. Here we can we could use u sub and get rid of this whole thing and say that u is equal to t over t plus 1, or we could use the rules for logs. The rule for logs that we can use is this quotient, where we could separate the terms of the quotient into two terms of a difference. So the natural log of x over y is the same as natural log of x minus natural log of y. So the natural log of t over t plus 1 is the same as the natural log of t minus the natural log of t plus 1. And so now each of these we just take its derivative. This one's easy, because this is just the natural log definition. The derivative of natural log of anything is 1 over that thing. So it's 1 over t. This one, we'd have to use the chain rule, because we know what this derivative is, but this derivative is slightly different. So we let u equal t plus 1, so that the derivative of ln u is 1 over u. And then we have to take the derivative of t plus 1, which is just 1. And so we get the 1 over u, substituting back the t plus 1, we get 1 over t plus 1 times this derivative, which is 1. So you get 1 over 1 over t plus 1. So the two derivative terms is you have 1 over t minus 1 over t plus 1. You can keep it like that, or you could put them under the same denominator, some common denominator, but you could leave it like that as well. Alright, switching gears now. We've taken care of what essentially in college would be your first semester of calculus, dealing with differentiation. So again, that was a very quick and overview of derivatives, but it gives you an idea of some of the things that you'll need to look out for. But in the second semester of a calculus course in college, you learn about the antiderivative and the process of integration. So this is something that over the course of the year, I expect students to get increasingly better at, but this is in an effort to let you see this for the first time, so you can recognize some of the notation and some of the procedure. But we will certainly do a lot more with this as we go on solving problems throughout the year. I mentioned at the beginning of the video that integration is linked to finding the area under a graph, which is often useful for many different things in what we do in physics, just like how taking the derivative is linked to finding the slope. The integrating will be the inverse operation of finding the derivative. So if you took the derivative of something, you would get a function. If you want to go back to the original function, you'll have to integrate or find its antiderivative. So, but I want to make sure we can link this to the fact that what the integral tells us is the area under a curve. So let's start out with this graph here. So really this is the graph that represents y equals c, where c is a constant, so it's the value c the entire time. And the area is infinite, it can go on forever. But if I just close it off at some value a, and I ask you to find the area of the shaded region, how would you do that, and what is the answer? Well, that's pretty simple. Once I've closed this off and I want to find the area from 0 to a, what I notice here is I've created a shape now, a rectangle, whose area is length times width. And so the answer to this question is the quantity CA, C times A, length times width. Now, as I said, the area can be infinite, so A is just a number, but what if we don't put a bound on it? Well, I could choose any value of x so that the area now is Cx, and this now becomes the area formula. So the area formula Cx will tell you the value of the area for any value x if you have a graph y equal to c. So I want you to make this connection here. So if f at x equals c, then the area of x as a function of x is cx. Alright, let's take a look at this graph. So this time we have a line, which is represented by this function f at x equals some constant, the slope c times x. And I want to find the area under the curve. How do I do that? Well, if I close the area off here at this point A, then I can see that the area that's made under the curve is a triangle. So I use the area formula for a triangle, 1/2 base times the height. So it's 1/2 A times B, where B is the value, is the y value for that corresponding A value. But similarly, what if A had no bound? Then A would equal x. But here, the height is no longer B, so that's a little bit different than our rectangle. The rectangle always had the same width, but we were changing the length. But now the height of this triangle would also change as we make the base larger. So we knew that B was the function evaluated at A. So if A equals x now, we just want B would be represented by the function itself, because it's the function evaluated at x, which is Cx. So the new area formula, half the base times the height, the base being x, which takes us off to whatever x value we want. The height would be the corresponding value of the function evaluated at x, which we could substitute in Cx. And if you simplify that down, you get 1/2 Cx squared. So again, similarly, I want you to remember, make the connection here that when the function is f at x equals Cx, then the area under this function is 1/2 Cx squared. Okay? Hoping you might see some connection here. Now, what about this? This was a problem that Newton himself struggled with, trying to figure out the area under a curve like a parabola. So we have that f at x equals Cx squared. It's not the shape that is, if I close off the space under the curve at some value a, the shape that's made here is not some geometric formula that we have right at our disposal, like the rectangle or the area of the triangle. So we have to try to use what we know. Now this might seem a bit abstract, but you'll see that it's a process that does work. So one thing that you can try to do is section off pieces, slices underneath of this curve. And for simplicity, we'll make the base of each of these slices the same. So if we just take one of those slices, let's say from this value x1 to x2, whose difference is what our delta x is, this is close to being a rectangle, except for the fact that it's not. So, and that's because the height of this line is different than the height of this line. But if we were to make delta x increasingly smaller and smaller, the height of this line would get closer to the height of this line. And the closer those two lines become similar in height, the closer it becomes to being a rectangle. And then we could simply just do length times width. And that would be for one slice, and then the area under the curve would be the sum total of all those slices. So this seems like a process that we have looked at before, a limiting process, a process by which we take a term like delta x and we try to get it to go closer and closer to 0. It's not practical to say let's make delta x equal 0, because if it has no base, it has no area. Just like we can't, when we took 2 points and try to find the slope, if we actually put the points on top of each other, where if you do rise over run and the run is equal to 0, then you can't find the slope. The slope is undefined. So you have to use this limiting process. So we say that the heights of the two lines will equal at the limit when delta x approaches 0. So we'll make the area of one small strip equal to dx. So remember when we swapped out delta x for dx, where d before standard for derivative, differential just means very, very, very small. So because we are limiting, we're making delta x closer and closer to 0, so we could either choose to use the limiting notation, or we could replace delta x with dx. Okay, so the area of a very small strip, one of these strips here, that's what d area means, is equal to the limit as delta x approaches 0 of the area of a rectangle, whose length, let's just say, the length is vertical, is the value of the function, which should be the same on either side because we make this interval so small. It becomes 0, and the width is delta x. So we'd have to continue to write the limit factor here, term, if we were going to use the delta x, or we could replace delta with d, and that makes it a little bit easier. So the area of one small sliver is the value of the function times dx, which is a tiny strip, the base length of a tiny strip of area. Now we want the total area, so we have to add all the strips together. And for that we use the sigma notation. So the total area is the sum of all the small areas. Now we can replace the little area notation with the limit as delta x approaches 0 of the sum of all the let's see here. So it's the limit as delta x approaches 0 of the sum of the value of each function at various positions along the graph times the delta x, which is, again, equal base lengths. But depending on where you are, what the value of x is, that's going to determine what the height of the function is. So you do have to specify that there's going to be different values of x that we're dealing with. But what are the bounds of this sum? Well, how much you want to add depends on how much area you want to find. So for this particular example here, the bound is from a to b. So the way you write that is the limit as delta x approaches 0 of the sum from I equal to a to b of f at x at I delta x. Okay? So this is saying that we're going to make strips of rectangles, which they're only rectangles once we let delta x get closer and closer to 0. And we're going to sum all of them up from the left bound of A to the right bound of B, and we're going to sum up all those areas. Easier said than done. Well, if I'm making delta x really, really small, there's infinitely many strips that you could make under that curve. So we're not going to actually count them, although in your calculus class you might be asked to actually cut the graph into small strips and find the area of each strip, and that can be very tedious. But we're going to use calculus for this. In order to see how this plays out, let's look at the two examples we've done so far, specifically the results of those two examples. We showed that if you have a function c, which is a constant, the area function that goes with it is cx. If you have a function cx, its area function is 1/2 cx squared. So knowing what we know about calculus, specifically derivatives, we can see a pattern begin to show with these two examples. Can you see it? If you could tell that taking the derivative of the area function gives you the original function, then pat yourself on the back. So the derivative of our area function is equal to our f at x function. So if we knew the area function, we could take its derivative to find the curve, whose area is determined by the area function. So if we had started with the area function, we could take its derivative and know what kind of graph produced an area like the original function we had to begin with, the area function. But what if you have the original function, you want to find the area? Then there's got to be a way to undo this. Multiply both sides by dx. So if you do that, on the left you get d area equals f at x dx. Well, this goes back to the area of our little strip. So to find the total area, we just need to sum all the strips together. So some new notation again. when we change delta x to dx, then we're also going to change the sigma sign. Now sigma in Greek is the capital S. So a contemporary of Newton, Leibniz, first started to use this symbol, which is just a script S, which he had originally used as a abbreviation for summa, which is to add, the sum. So this is really what we call the integral sign is really just a long script S, short for sum. So we are going to replace sigma with the integral sign because we're not going to actually discretely count and add all the little areas. So the area of x is equal to the sum, or in this case the integral, of f at x dx. This is called an integral. And the process of finding the area is the process of integration. So here our function is x squared. We know that the area function is some function whose derivative gives us x squared. So the question we want to ask is, what derivative gives the result x squared? Well, if you think about how the power rule, how a derivative is taken by using the power rule, we bring the power down and we subtract the power by 1. We basically want to undo this. So here we're going to add 1 to the power and then divide by that new power. That should reverse the process. So we add 1 to n, and then we divide the whole thing by n plus 1. So here we have x to the n. I'm going to use capital F at x to stand for area, because that gets to be a little bit tedious to keep writing. So capital F at x equals the integral of f at x dx. So we substitute in x to the n, and so the solution to this problem is whatever the function is when you take its derivative, you get x to the n. So we add 1 to n, and then we divide by n plus 1. Or you could leave that as a fraction out front. But notice the dx is gone, the integral sign is gone, because we've performed the process that we were set out to do. We know that this is true because the area under this function is equal to this if and only if I take its derivative to get back the original function. And that's true. If you take the derivative of this, bring the power down, subtract the power by 1, you'll get x to the n. Now, there's one thing that will constantly be monitored by your calculus teacher at this point. There is something missing here. And this comes from the fact that there is the constant rule for derivatives. There's nothing to say that there could have been a constant here, that when you take its derivative, the derivative of this term plus the constant, you still get back this because the constant just goes away. So that's a technicality. You can add a constant here and still have the appropriate result. So you consider the two functions x squared plus 1 and x squared plus 2. Their derivatives are the same. They're both 2x because the 1 and 2 go away. When you take their derivative, you get 0 for both. So if you think about geometrically why that's true, these numbers don't change how these parabolas are sloped. This is just shift up 1 and this is shift up 2. So the way in which the slope changes remains the same. It's just the position of the function on the graph is different. So the constants just go away. So if we try to go backwards, you won't know what that c value is. If I tell you that your function is 2x, what's the antiderivative? What is the integral? You would certainly be able to get me the x squared part, because I add 1 to the exponent. That gets me 2. Divide by that new exponent. So I divide by 2, I get x squared. But I wouldn't be able to tell you if it's a plus 1, a plus 2, a plus 0. I wouldn't be able to tell you. There's not enough information. You actually need to be told. And there's no other way of determining that. You have to be told. These are called initial conditions. You have to be told what that constant is, or else you indefinitely know the function. You don't know you haven't ruled out all possibilities. There's still a range of functions that could exist with different constants tagged along. So for now, what we do to account for it is we add c as a constant. So consider this to be a new rule. The integral of x to the n dx is equal to 1 over n plus 1, x to the n plus 1 plus c. This is called an indefinite integral. Indefinite because we don't know what the bound is, and we don't know what this constant could be, which we call the constant of integration. It is the reverse power rule. So we originally asked the question, what is the area under this parabola? We're finally ready to answer that question. We want to find the integral of x squared dx. That is essentially saying what is the area under the x squared graph. And so for that, we're going to use the inverse power rule. Our power is 2, so it's 1 over 2 plus 1, which is a third, times x to the 2 plus 1, which is x cubed, plus c. So there we have it. The integral of the x squared function is equal to 1/3 x cubed plus c, where c could be any number. How about if we knew what the bounds were? I want to go from a to b. Well, the notation wise, you need on the integral sign, you place the bounds on the right side. The lower bound, or the left bound, is on the bottom, and the right bound is on top. So if we were looking to find the area between A and B, we could use the fact that once I know the area formula, I plug in either the value A or plug in the value B, and I'll get the total area from 0 all the way up to whatever value I plug in. So If I were to have plugged in just the value b into my area formula, I'll get the area from 0 all the way up to this right bound of b. If I plug in a instead, I'll only get this much area. But to find the area in between, we just want to subtract the two areas. So you subtract this big area minus this small area, and it'll leave you with the area in between. This is called the definite integral. So if we integrate from a to b, f at x times dx, you'll get the integral function evaluated at b minus the integral function evaluated at a. So let's find the area under x squared, but from the values 1 to 2. So we write it integral from 1 to 2, x squared dx. We know that the antiderivative of x squared is 1/3 x cubed plus c. So we did that. We used that new rule of ours. We don't need to carry the integral sign or the dx anymore because we've taken the integral. But we still have the bound. So what's common to do is to add this line with the left and right bounds still attached. So this is just like a vertical bar. And now we have to find this value, the area formula evaluated at b, in this case 2, minus the area formula evaluated at 1. So you can see here that if I substitute it in, because I'm subtracting and I distribute the negative, on the left here I have a plus c, on the right here I'm going to have a minus c. So the c's cancel. So when you're doing a definite integral and you know the bounds, the plus c doesn't matter. So for instance, up here, if I knew I was doing a definite integral with bounds, that's the only that would be an occasion where I don't need to write this plus c, because when I evaluate it, I am going to lose the plus c. And so what I'm left with is just 8/3 minus 1/3, and I get 7/3. And that is the area under x squared between the values of 1 and 2. Alright, so for u sub here, I'm only going to go over one example just so you can see how we can use u sub in reference to integrals. So we've done it before with derivatives, now with integrals. So let's say we had an integral like sine 3x dx. So we go back to our special derivatives and realize that if I know the derivative, I can figure out the antiderivative. So as an aside, I know that the sum or the integral of sine of x is minus cosine x plus c. Why? Because the derivative of cosine is minus sine. But this sign doesn't have a negative to begin with. If there was a negative here, then the integral of minus sine, I forgot my dx, equals cosine of x plus c. All right. So I know the integral of sine of x is minus cosine x plus c, but I don't have sine of x. I have sine of 3x. So the 3x is the problem. So we say let u be 3x. And so now I have my integral of sine of u. But where I have a u here, I want a u here. I can't have dx, I have to have du. So how do I find out what du is? I have to come over here and find a derivative. If I find the derivative of u with respect to x, I can solve this expression for du, or for in this case for dx, and substitute that in to my formula. So let's see how that works. So I'm going to take the derivative of this with respect to x, which is just 3. So then I get that du equals 3 dx. And so divide both sides by 3, I get that dx equals du over 3. So that means that dx can be replaced with du over 3. Now the over 3 part just becomes a multiplier. So we could just pull that out of our integral and write this as 1/3 integral sine of u du. And we know the answer to this problem. The 1/3 comes along for the ride, and we get sine, that's minus cosine u plus c. But where we had u now, we put back the 3x that we had before. And so we get minus 1/3 cosine 3x plus c. That's our integral. So that's how you use u sub for integrals. Lastly, I'm only going to make just a quick comment about differential equations. This is pretty advanced stuff, but it does appear on the AP exam, and so we do have to talk about it at some point. Although, again, we're going to use more of in-class time to go over this stuff in a lot more detail. But differential equation is essentially an equation with derivatives in it. So a place where you might be likely to see that is if you take this question. What if acceleration was a function of velocity? So let's say that the acceleration equals b, which is a constant, times the velocity. And I want you to find the velocity as a function of time. Let's assume that the object starts with some initial velocity, VO, at time 0. Okay. Well, right now, this isn't a differential equation. The way you make it into a differential equation is by replacing one of the quantities with a derivative with respect to time. So we introduce the derivative by saying that the acceleration is the derivative of the velocity with respect to time. Acceleration is the change of velocity over time. So by putting dv by dt in for a, we get dv by dt equals bv. We've just made a differential equation. That equation now has derivatives in it. There's different ways you can rearrange the terms, but that is now a differential equation. Now to solve it, what we want is to find velocity as a function of time. So in this next step, we call it separation of variables. V and t are your two variables that we care about. V is dependent, t is independent. B, this letter B is just a constant. It doesn't matter where that goes, really. So I'm going to leave it on that side, but the V has to go on the same side with the dV, and the dt needs to come up top. So I bring dt up, I divide both sides by V. So I get dV over V equals B dt. I did nothing but rearrange, but now I have the V with its dV on this side, and then dt is on this side. If there was any other t terms, it would have to be on this side. Multiplied or divided. If it was added or subtracted, that's a whole other issue. And then we have the constant, which just comes along for the ride. Step 3 is to integrate both sides. We integrate the left and the right and put their appropriate bounds. So on the left, the bounds are so on the left side we go from v initial, VO, to the velocity at whatever that later time is. So it could be sometime later, we don't know, just let it go for an extended period of time. The time begins at time 0, and again also goes for an extended period of time. So we're going to take the derivative of both sides now. This is like a 1 over x. So whose derivative would give you 1 over x? That's the natural log. So on this side you get the natural log of v, which needs to be evaluated from 0 to v at t. On the right side, there is no variable. So technically it's just dt, but out front of there you can imagine there's a 1. So whose derivative would give you 1? That would be just t by itself. So I have bt, and that's evaluated from 0 to t. Step 4 is to evaluate. So we have to plug in our limits of integration. So on the left side, it's the natural log of v at t minus the natural log of v0. And that equals b times t minus 0. So I plug in t in for t, and I get t. Plug in 0 in for t, I get 0. So on the right side, you get just bt. But remember now, we're looking for v at t. So there's two things that we could do. First thing is going to be using a log rule to simplify this difference. And then we have to solve for v at t. So here we have, using the log rule, the difference is the same as the natural log of the quotient of the two terms. And that equals bt. To get what's inside the log out, we have to use the base e. So if we take both sides, what you do to one side, you do to the other. So if I use the base e and put this term into the power, I can unlock what's inside of the log. So if we use this rule, we get e to the natural log of v at t divided by v0 equals e to the bt. Applying this rule releases this term from inside of the log. But now you're left with the exponential on the right side, and the final step is to bring v0 onto the right, and you now have v as a function of time. What if you didn't know the bounds on your integral? Well, We go back to the step where we integrated before we actually plugged in any of the bounds, which was this step right here. And we take the integral, and you only need to use a plus c on one side because the constants can always combine together because they're just numbers and form a new constant. So we'll just use plus c on the right side. So you get the natural log of v equals bt plus c. That's just integrating both sides. Then to solve for v, you use the same natural exponential trick, and now you get that v equals e to the bt plus c. Now the plus c is on top. If you want the plus c to be something that is, let's say, on the bottom, you could separate the two terms in the exponent by multiplying two base e terms. So I have e to the bt times e to the c. That's the same thing as this. And now e to the c is just a number. Now, that should be the same thing as what we did given our specific bounds. The criteria was that if at time 0 the velocity is v0, then if we compare the two formulas, v0 would have to be equal to ec. So does that work? Yes, it does. We plug in, set this equal to v0. When t is 0, e to the b times 0 is e to the 0, which is just 1. And so all you're left with is e to the c. And so since that is true, we know that our integrals do match under those conditions. So that is all the time I have for this crash course video. I hope that you can take away a lot of information from this video. Be sure to look over those rules, go over all of the examples that were discussed here, and try to create some problems for yourself to do. And be sure to ask questions if you have them. All right, signing off. Goodbye.